introduction. My name is Hao Guo, and I'm from Tsinghua University. So today I'm going to talk about my work with Yi Jing, Yuanshen Pan, Xiao He, Bo Rugong, and Jing Tai Ding. It's about the practical and theoretical correct analysis of VOX. So VOX is a NIST additional first round submission signature to the NIST, and it is one of the 7 UOA-like schemes. So we will first talk about what is VOX, and after that we will talk about the min rank problem which we used to solve the to give it an attack, and I will talk about our attack, which the first part is practical attack, and the second part is another theoretical attack. Okay, so what is UOA? And I think the previous presentation talks a lot about UOA, so I will just skip it so quickly. So UOA mean in UOA we have oil variables and the vinegar variables, and the vinegar variables they have quadratic terms, and for oil variables they are only linear terms and bilinear terms with the vinegar variables. And in the UOA system, the number of equations is equal to the number of oil variables, and the number of vinegar variables is usually larger than that of oil variables. Otherwise, we will have the Kipling-Champney attack. And the UOA central map, if we write it as a matrix form, it has this shape where the bottom right part is the zero matrix with O by O, and the other parts are I write it here for the symmetric form, so you can see it as a quadratic term, and this will together with a secret key, secret linear map S from FQN to FQN. This will together make the public key of UOA, and the work of S is to mix the variables together and to make it difficult to distinguish between that. So from the UOA, we now move to the UOA hat plus. So what is UOA hat plus? The UOA hat plus is mainly about changing some random polynomials to change some oil vinegar polynomials into the random polynomials. As you can see in this picture, if you can see it as slices tapping together, and the first T part will be represent the random matrices, and the last O minus T part will represent the oil vinegar one polynomials. And since the polynomials are never different anymore, so they are not different, they are not the same, and we need to make a mix of the polynomials. So there is another additional random linear map T, which is applied to mix the random polynomials with the structured oil vinegar polynomials. And the public key of UOA hat plus is P, which is T composed with F composed with S. And this is UOA hat plus. So to solve this UOA hat plus, you need to you can also fix the vinegar variables and then try to solve a linear and also a quadratic term. You can see in the T part, because if you fix the V variables, there will be O variables left in the first T part. So this means we will have to solve a small quadratic system, which means T should not be too large. Okay, now come for the QR variant, which is also applied by the VOX team. So what is QR variant? This also appears in the QR UOA, I think. And the idea, I think, is to substitute each C by C block of the matrices introduced in the secret key and public key into a matrix of the form phi A for some A in the extension field. Its main use is to compress the public key and the key size, and as we'll see next, in the next page. So from the central map of QR variant, we can construct an equivalent UV hat plus instance. And in this instance, the number of equations will be the same, but the number of variables, I mean, vinegar variables and the oil variables will both drop. And if we make a pullback here, we'll find the bar F polynomials, which corresponds to the changed keys in the extension field. And yeah, so what it works is just UV hat plus combined with the QR variant. So as you can see in this picture, we have we have this UV hat plus shape structure, and we do a central map F bar of VOX with some smaller V and O's and in the quadratic and in the extension field. And this is the recommended parameters of VOX, and the last column is their claim security. And and you can see here they are using very aggressive O and V here. And if you remember that the number of equations is big O times C, then you will find that there are too many equations here, and it gives us some chances to attack this. Okay, so now for the min rank problem. So what is min rank problem? I think many of you knows about it, but I will repeat. And min rank is to solve for the linear combination of given matrices that can give you a special small rank. And in this case, the matrices are generally 4-rank matrices, and this problem has been shown to be NP-hard. And how to solve it? So for n by n matrix M, there are 3 main methods to solve for the min rank problem. The first, they are all correspond to different representations of the rank condition. So the first is a minus method, which is naively calculate the R by R minus of the matrix. Sorry, R plus 1 by R plus 1 matrix of minus of the matrix. And the Cryptanalysis method is to calculate the n minus R dimensional kernel space of the matrix. And finally, we have the support minus method, which is as you can think about it as making a matrix M to be S times C, where S is the M by R matrix and C is a R by N matrix. And we can formally write out the R dimensional row space of the C matrix, and where we calculate the R plus 1 minus of the augmented matrix, we can get bilinear equations for the linear variables and the minor variables. And for minus method and Kimni-Shamir method, we all usually consider the way of solving it by using Grover basis, and we consider the ideal generated by these equations. And for support minus method, the authors recommended that we should use bilinear XL algorithm, which multiplies monomials to equations, and so for the linear system of the monomials. And and here comes our attacks details, and I will skip some of the technical details, and if you are interested, you can ask me after the talk. So our idea is to try to find some rank defects in the matrices, but how we should find it. The first idea is to say we take out the last column of every matrix and every secret key matrix and combine them together to form a new matrix. Then this new matrix will have a rank at least at most V, because this part is some random things and this part is all 0. So this is for U over, and this long side is the number of equations M. So this is trivial because V is larger than O, and Then now we go to the second step for the central map of UE hat plus. You remember that in the hat plus variant, there is a T random part here, which means that first T polynomials are random polynomials. So the corresponding terms here are also random numbers and not zero. And we have that the number of the rank here is considered to be two parts. The first part is the upper right part, which contributes to the rank of V, and the bottom left part, which contributes to a rank of O or T, which is the smaller of it. And in this case, in the case of VOX here, we are considering the case that here, since it's V is larger than O minus T, so this matrix will have rank at most V plus T, and this is also trivial. And here we apply the QR variant here, and for the central map of VOX, and we have big V equals to small v minus divided by C Winiger variables, and big O equals to small o divided by C Euler variables. And here we found that the number of V and O, here V and O are small, and if we compare these values with T, we may have a choice, may have possibility to find a not full rank matrix here. But and this is exactly the attacks given by Fluye and Ikematsu in their papers. And the VOX parameters the VOXes submitters, they change their parameters to adapt to this attack, and they have O, which is smaller or equal than T. And so if they try to use this, then this matrix will have rank at the most V plus O, and this will again be a trivial thing. And here is a recap of the parameters of VOX, and you can see here the O is always smaller or equal than T here. But however, we have that 2O is larger than T. This gives us a chance to make the following attack, which is to combine two such matrices together. And this can be also viewed as you take two rows of two columns of each matrix and combine them together, and you push them together and make the 2n times O matrices. And since we are having the first part, the upper right part here it has a rank of 2V, because as you can see here, V is small and O is large. And for the down left part here, we have 2O is larger than T. So this part will give a rank of only T, which means the total rank of this matrix will be at most 2V plus T. And this is a non-trivial thing for now. And to adapt to, and we are using the central map matrices to construct the target matrix we want, and to change it into information or a problem about public matrices, we need to use a formula which shows that the transformations of the rows and columns of the public matrix, public key and the secret key are consistent, which means we can find such pair of S and T's such that this equation holds. And we can, this equation should be interpreted as you can apply the S minus inverse transpose to the coordinates of P tilde 1, P tilde n, and make it as the linear combinations of these Pi tildes. And so there exists some x1 to xn, y1 to yn, which are forced in the extension field, such that this equation holds, and that this means that the left matrix has a rank of at most 2v plus t. And at this step, we have a min rank problem here. So recall that we have two main methods to solve for the min rank problem. One is the Cryptanalysis method, and the other is support minus method. And for the minus method, we will just ignore it here because it is sometimes not that efficient. And in general, the support minus have lower complexity estimations than the Cryptanalysis method. However, and we first tried to use support minus, but it did not work very well. And the memory just blows up, and it did not work very well. And however, the Cryptanalysis method was very efficient, and we use it to make a practical attack here. And we use Cryptanalysis method to transform this min rank problem into a system of quadratic polynomials, or I should say bilinear polynomials over x, y, and additional variables in the kernel variables. And let R equals to 2v plus t. And we know that since the target matrix is a 2n by O matrix and it has rank R, it should have the dimensional 2n minus R left kernel space. And our matrix equation is presented as follows, and from which we can get 2n minus R times O quadratic equations. And we try to use magma to solve for these equations, and the result was pretty good, I should say. And we are getting lower than 1 hour, and we solved all these instances. And you can see for most of the instances, only 1 second or 15 seconds, smaller than 15 seconds is needed to solve it. And the memory usage is not that large. And I think this is a very, very practical attack, in my opinion. And so the question here is, how should we understand this attack and why it works that well? And we do not have a very clear interpretation here, and I will give not that explanation that is not very good here, but it somehow captures the complexity here. And we are using the work of Nakamura, Wang, and Ikematsu, and they introduced a degree which is the smallest total degree of this series, and we can use this series and to look at these coefficients and try to find the lowest degree where they believe that this degree is bound from above the solving degree and gives an upper bound for the complexity estimation. And we try to apply the solving degree here, and from the formula before about from the previous page, and the complexity here is not that close to our results. I mean, if you have an algorithm that runs at about 1 hour, and then it should have a complexity of about 2 to the 40s, I think. And here and also in the magma experiment, we found that all the solving degree are 3, and this is pretty astonishing. And I should say, we try to revise the complexity here, but it still does not fit with the running time here. And we think it is challenging to give a clear understanding of why this attack works. Okay, and here is another theoretical attack, which was first found by my co-author Yi Jing, and she says that if we have the QR variant here, and the QR variant means to substitute each C by C matrix into a special form to compress the size of the public key. And she found that if we can have C equals to C1 times C2, which is a composite number, and then such C by C block can be divided into small blocks, and there is a transform that is compatible with such division and subfield structure. Therefore, we can interpret the previous attack of Fluid and Ikematsu to this equivalent UV hat plus instance over FQ to the C1. And we are having C2 Vinegar variables and C2O Voil variables here. And as long as we have C2O is larger than T and C2V is smaller than O minus T, then this attack will be applicable. And here is some complexity analysis and for this attack, and we did not perform any practical attack on this because we think the previous one is good enough. Okay, so here comes the conclusion. So we break all the parameters of VOX completely and using Cryptanalysis method, and we think the theoretical analysis of this practical attack is still on the way. And I should say that the VOX team, they adapt to this attack and change and they abandoned the QR variant and they changed the name to the name Fox. And I think the next step is to maybe try to look into it and see how it works and how to attack it. And that concludes my presentation. Thank you.
So maybe one or two quick questions, maybe.
Thank you for your nice talk. Regarding the support modeling attack, can you say a little bit more? Do you understand why it's not better than the Kipnis-Shamir attack?
You mean support minus attack and Kipnis-Shamir attack?
Because in theory, you have better asymptotical results.
Yes, I mean the support minus attack, they have better time complexity in general, but they have large memory cost here. For example, for the I should take this one. So if you see this one, it has if I remember correctly, it has the matrix is a 54 by 26 matrix, and the target rank is 20, and so we can take about 21 to 26 rows, and we tried it, but I mean if you take more rows, the solution is more possible to give only one, but the number of variables just explodes, and if you take not that many columns, then the solution maybe not work very well, or that it may not. It may not be the case that it can give a unique solution here. So this is why we are not using using supporting minus here, and I think that maybe you can try it. I don't know. I should say that at least for my case, it does not work very well, and I think I'm somehow satisfied with the result of the Kipnis-Shamir method here. Okay, thank you.
Okay, let's thank the speaker again.